Hello, and welcome to today's PSU Transportation Seminar. My name is Jason Anderson, and I will be introducing and moderating today's seminar. Our PSU Transportation Seminars have been a tradition since the year 2000. There we are. These seminars are once again being held live on Portland State University's urban campus, located on the ancestral homelands of the Multnomah, Cathlamet, Clackamas, Tumwater, and Watlala bands of the Chinook, Tualatin, Kalapuya, and many other indigenous nations of the Columbia River. It is important to acknowledge that we are here because of the sacrifices forced on the indigenous ancestors of this place, remember these communities, and to honor their legacy, lives, and descendants. So today we are pleased to have my friend and colleague Sirisha Kothuri presenting on active transportation counts from existing on-street signal and detection infrastructure. Sirisha is a senior research associate in the Department of Civil and Environmental Engineering here at Portland State. Her primary research interests are in the areas of multimodal traffic operations, bicycle and pedestrian counting, and safety. Here's an overview of our upcoming seminars. You can find the registration links on the TREC website. We hope to see you participating. As an overview of today's seminar, you can expect our speaker to present for about 40-ish minutes, followed by a Q&A. We will be receiving questions through the Q&A feature on your control panel, and we'll ask them at the end of the presentation. If we run out of time for all your questions, we will give our speaker the opportunity to email written responses for any questions left unanswered. We have enabled closed captioning, but you must click on the CC feature on your control panel to view them. We will be recording today's webinar. It will be available on our website later today, along with the presentation slides. If you are tracking professional development hours, this webinar is eligible for 1 hour of continuing education credit. With that, I will hand it over to Sirisha.
Thanks, Jason, and good afternoon, everyone. So today I'm going to be talking about this project that we just finished, and it was funded by the Oregon Department of Transportation, and it was on active transportation counts from existing on-street signal and detection infrastructure. So before I jump into the presentation, I just wanted to take a moment to acknowledge the rest of my colleagues on this work. Patrick Singleton, who was the co-PI on the study from Utah State University, Mahyar Vahedi, who's a graduate research assistant at Utah State, and Elizabeth Yates, who's in the room today, and she's a graduate research assistant here at PSU. Okay, so before we talk about getting active counts from signal infrastructure, we need to talk about why we need to count. We need to count for a variety of different purposes. We want to be able to track changes over time. We want to be able to plan and design new infrastructure. We need counts for different kinds of analysis. For safety analysis, we need it for the exposure metric. And then we also need it to conduct any health analysis or equity analysis. The counts are really important, but there are a few challenges with pedestrian counts. So pedestrians are less confined to fixed paths. They have unpredictable movement. So if you're thinking about someone who's in a crosswalk, they can, deviate from the crosswalk and take the shortest path to the curb. So that makes it really difficult for especially automated equipment to count them. They also travel in closed groups, so occlusion is a real issue with automated counters. And then there are challenges with limited equipment being available to count pedestrians, especially at signalized intersections. So this slide here shows all the automated equipment available. You can see there are a lot available, and they run the gamut from manual counts where you stand in the field and count pedestrians or bicyclists using a clipboard. You have video, you have all your infrareds and others, but cost is a real consideration, especially if you want to have counts all across the network. So systemic pedestrian counts are definitely a challenge. There are some emerging technologies that have come to the fore in recent years. So you have your Bluetooth and Wi-Fi readers that can be used to count pedestrians. You also have your passive crowdsourced data sources like Streetlight. So Streetlight's a data source that basically uses your location information on your smartphone, and they can impute your mode based on that. If you cannot count, then you use your modeling, right? So you have your direct demand map models, which use your land use and built environment characteristics and socio-demographic characteristics. Or you can use your regional travel demand models, but these typically do not include the level of detail that we would like. So we have this new data source, and that is the pedestrian push buttons. So these are fairly ubiquitous, right? They're present at most signalized intersections. These are active sensors, but they're imperfect. So they give us measures of activity, but we really don't know how many people are there at the intersection. So one person can press the button multiple times. You can have a group of people pressing the button once. You can also have people crossing without pressing the button. We've all done it when there is no traffic around. And in certain situations, like here in downtown Portland, for example, you do not have any push buttons at all because the signals are on recall. That means that the walk indication will come up every time without you having to push a button. But these push buttons, where they're present, give us an opportunity if we could figure out a way to convert these actuations into volumes, because every time a push button is pressed, you do get the note of it in that log that you see right there. So there have been a few push button studies that have been conducted in the past. Some studies have looked at push button rates and how they vary across locations and signal type. So these rates vary by the presence or absence of approaching motor vehicles. So again, as I said, if you do not have motor vehicles, for example, people may just cross without pushing the push button. And so that could cause the rate to vary. Age, gender, and other pedestrian characteristics can also influence the usage of push button rate. There has been some initial analysis done on push button actuations. One study had looked at using actuations for understanding patterns, so time of day, day of week, seasonal effects, and special events. And some other early studies have looked at developing these adjustment factors for converting these actuations into volumes by recording video data, and then using that to correlate with actuations. So in those studies, the adjustment factors varied between 0.84 and 1.21 pedestrians per phase. And the observed correlations were between 0.8 and 0.83. So those were pretty good. But these studies were limited. They were conducted at one intersection, and so were just proof of concept. So a large study conducted in Utah a few years ago recorded videos at 90 signalized intersections and across 320 crosswalks. So they collected a lot of data and captured almost 175,000 people walking at these locations. And so they used all this data and correlated that with the actuation logs and were able to get these volume estimates. So the objective of our study here was to basically see if we could replicate that for Oregon. We wanted to examine the feasibility of doing that here, develop adjustment factors to convert those actuations into pedestrian counts. And then we also wanted to determine the transferability of methods. Can we transfer the model estimated in Utah to Oregon and vice versa? So can we transfer the model estimated in Oregon to Utah? So that would give us some idea of whether we need to undertake this model building exercise every time, or could we just use a model that has already been developed? So to start off, we first had to assemble an inventory of sites. we sent a lot of emails to a number of agencies in the region, ODOT, PBOT, the cities of Corvallis, Eugene, Salem, and Washington County. From them, we got a list of 803 signals, and then we down selected to 433 signals based on some criteria. So the criteria we used were that these signals needed to be in the Willamette Valley or close to Portland, and this was just because we wanted to facilitate the ease of data collection. We also selected signals that were recording high resolution data because we needed access to those logs. And then they needed to have some evidence of pedestrian activity. So we defined that as having at least 10 or more actuations per day. And then we could do that by looking at the logs. Once we had those list of sites, then we used GIS to append a lot of other characteristics that we would be interested in that would affect pedestrian demand. Transit stops, AADT, number of lanes, and other characteristics. Then we ended up choosing our sample using a stratified sampling, and then we used the ODOT place type variable, which sort of includes the built environment land use context. And we divided the pedestrian activity into 3 categories: low, medium, and high. And again, this was based on the actuations that we were seeing in the logs. So our goal with the sampling process was to ensure that we had a wide distribution of sites. So we ended up finally looking at 49 sites, and these were distributed across the different place type contexts as well as the different pedestrian activity contexts. So here's a map showing our selected sites. These are 49 in total, and the different colors show you the different jurisdictions or agencies that these signals belong to. As we were working on this project, we also got our hands on a different data source. These were a set of 16 locations in Eastern Oregon, and these locations already had pedestrian volumes reduced, and those were available for either 16 or 32 hours. So we were able to use these 16 sites and append them to our study. So we had a total of 65 sites. So for the 49 sites that we chose, we had to collect video data. So we contracted with a local vendor and instructed them to collect video for 48 hours at each location. So the 48 hours was so that we could encompass the AM, PM peaks as well as the daytime and nighttime hours. So once we had all that data collected, we basically had a data extraction process coded, and for each location, we ended up creating a file in Excel, and it was through Visual Basic. So for each location, we had a screenshot of the location here to help the coders. So we had the crosswalk names marked at each location. We also had the directions listed, so that would enable the coders to enter this information easily. For each file, we locked the intersection ID and intersection name, so they didn't have to enter that. That would reduce their burden. And then we had them record all these categories. So to record them, we had the options as drop-down lists. So the coder, as they're watching the video, could pick out the crosswalk name, the direction of travel. We also recorded whether the user was a pedestrian, bicyclist, wheelchair, skateboard, scooter, or other, and the number of users crossing at the same time, as well as the date. We also recorded a couple of timestamps. The first timestamp is when the pedestrian steps off the curb and into the crosswalk to begin their crossing. And the second timestamp is when they step onto the curb at the other end to complete their crossing. So once we had all this data recorded for the 49 sites, we undertook a validation process. And the validation process was to ensure that the data we had was correct and accurate without any errors. So we had a trained researcher go through each of these files and randomly pick 5% of the records and cross-check them against the original video that the coders were watching. If there were any mistakes identified, those were corrected. And if there were any systematic problems that were found, we would undertake further validation. So once the validation was finished, we had the data set ready for modeling. So we looked at getting some descriptive statistics out of the data. So overall, we had 41,843 users at all these sites. We had over 35,000 pedestrians, over 5,000 people bicycling, and the other categories. The number of people counted by intersection varied widely. So for a location in Eastern Oregon, we recorded 5 users. And the maximum was over 2,600 users over the 48-hour period at this intersection in Portland. Overall, our mean was 658 people. Median was 388. So we then started looking at these correlations between the pedestrian actuations and the pedestrian volumes that we obtained from the video. So this plot here is showing the relationship with only pedestrians because we counted a number of users, right, at crosswalks. So this plot here is just pedestrians who are walking under their own power without any assistive devices. So what we see here is evidence of a nonlinear relationship. So we see an increasing relationship. So as the pedestrian push button activity increases, we are seeing some evidence of increasing pedestrian volume. Next, we looked at this UPED model. So here we are using an expanded definition of pedestrians. So pedestrians plus skateboard plus wheelchair users. And again, we're seeing very similar relationships. So increasing as the activity increases, increasing number of pedestrians. And here is the plot showing the total crosswalk users. So this includes everybody that were using the crosswalk in the video. And again, very similar sort of trends. We also looked at the time of day distributions from these actuations data. So the light gray lines here are the distributions from each location in our study. And the red line is the average across all locations. So as expected, we see that pedestrian actuation activity peaks during the middle and later portions of the day. And this is similar to what we would expect in terms of pedestrian activity. So once we had the data, then we're ready to model. And so we had a few data analysis principles that we followed. So we wanted to develop models that were accurate. So basically, that could predict pedestrian volume with little or no error and then little or no bias. So we did not want it to over or under predict. We wanted it to be generalizable. So with easy variables that could work as well on the out of sample data and in different places or times so that we could easily transfer it to other locations. We wanted it to be simple. Using only a few inputs and intuitive so that the variables and the relationships make sense. So with that framework established, we were able to define metrics for each of these categories. So we identified some statistical metrics that would help us to determine the accuracy of the models. We used a 10-fold cross-validation process to make sure that the model is robust, using a 90% training test, and then estimating our validation statistics on the 10%. And then we compared our results to the Utah study And then we also use just one signal related variable, which could be really easily calculated. And so I'm just going to go through these quickly so we can get to the results. Our unit of analysis in our study was 1 hour. So we are estimating the crosswalk volumes for every hour. And then our dependent variable here, we had 3 different dependent variables. And we did this because we thought that it could be useful depending on the application. So if you wanted to just get pedestrian volumes for some safety related applications, you could use the PED only model. But if you wanted all crosswalk users to understand how the crosswalk is being utilized or for signal timing purposes, you could either use the UPED or the total model. Our independent variables were different measures of signal activity. So basically, they were A45 and A90. These are the codes that you would get in the logs. A45 is when a pedestrian call is registered, and A90 is when a pedestrian detector is on, and the A, Bs, and Cs are just imputed values based on those codes. We tried a number of different functional forms to fit those non-linearities that we were observing in the data. So we looked at linear, piecewise linear, quadratic, cubic, exponential, and power. We also included an intercept in all the models. So this essentially means that we're still predicting pedestrians even if no push button was pressed. And we thought that is fine because there are people who walk without pressing push buttons. We also tried a number of different segmentations. So these are all the variables here. So we looked at whether or not the signal was in recall, so which means the walk indication will come up every time. Different levels of cycle length. So if the average cycle length is greater than 90 seconds or greater than 120 seconds, we looked at different peak periods, AM and PM peak. We looked at overnight hours, weekend hours, different ODOT regions to see if that made any difference. We looked at the different place types because that could have an impact on the activity. We looked at transit stops, so any transit stops within 400 or 800 meters. And we also looked at educational institutions, so within 400 and 800 meters. Okay, no, yeah. So as I mentioned, for the model validation, we adopted a K-fold cross validation process. So we've split the data set into 10 sections. We used 90% of the data to train the model, and we held out 10% of the data and then estimated the metrics on the 10% and used that to decide how well the model's working. So we did a randomized selection of signals for each fold. And then we used a different goodness of fit measures and accuracy measures to see how well the models were performing. So we followed a sequential search process. So we had 3 steps. So in the first step, we had a number of these dependent and independent and variables and functional forms. And looking at the metrics, we selected the best models, narrowed down the number of variables that we were interested in, and kept going through the process until we ended up with the final model. So in step 1, as I mentioned, we had those 3 dependent variables, PED, UPED, total. We had 8 independent variables. These were all our different signal metrics. And we had 5 functional forms that we were testing. So here are the results for step 1. So there are a few things that we were looking for. So we were looking for correlation. So this is the correlation between the actuations and volumes. So higher is better for these correlation statistics. And the others are the errors that we were looking for. And for that, lower is better. So in this case, for the 3 different model forms, there wasn't too much difference between the 3. So we decided to retain all of them for the next step. For the independent variables, we decided to proceed with this A45B and A90C. Again, these are those signal metrics that we imputed. And then we proceeded with 3 different functional forms, which are listed here: piecewise, quadratic, and cubic. So in the second step, we introduced these segmentation or interaction variables, and we were testing them. So in terms of our results for step 2, we found that the total model would be our model to proceed for step 3. And then between the A45B and A90C, we went with the A90C because of higher correlations and lower errors on some of the metrics. And then for the functional form, we ended up going with the quadratic model. We also looked at the results from the segmentation. And after this step, we ended up proceeding with 4 different variables. So we looked at recall, the cycle length, which is greater than 90 seconds, place type, and education based on the metrics that we were seeing. Okay, yeah, I talked about this. And so we went to the next step with that reduced set of variables. And these are the results using those segmentation variables. And here, although the place type and the educational variables were giving us lower errors and higher correlation, ultimately we ended up recommending no segmentation in the for the model, and I will talk about that in a minute. So these are the plots that are showing the data fitted in these segments, right? Sorry. Yeah, so for example, the blue line or the T line here is the fit for all those points where the recall is true. And the red line is where all the, for all the points where the signals are actuated or recall is false, and similarly, so on and so forth. We ended up not choosing segmentation because of some results that weren't readily explainable. So in this case, for the place type variable, for example, we were seeing fits for the low and non-MPO data points, and that prediction line was higher than the medium and high MPO. So that gave us some pause, and we really couldn't understand why that was. And we also had some concerns about the simplicity and interpretability of the results, and that since there was no large difference in model predictions, we ended up deciding to not move forward with the segmentation variables. The other issue was this whole aspect of lack of longevity and transferability. Place type is a variable that's very specific to ODOT, and so we were concerned about the transferability issues if we decided to use that in another state. Also, the definitions could change at any time, and so we wanted to use something that could be consistent. So the final results are recommended models. We kept the 3 just so that agencies would have a choice of the models to use depending on their need. We had 1 independent variable, 1 the quadratic functional form, and no segmentation. So these are our results from our final recommended model. So this is the model for the total all crosswalk users. Our goodness of fit statistics were very good. Our R-square for the total was 0.76. Our correlation was 0.86. And our errors were pretty low. So our mean absolute error was plus or minus 2.4 pedestrians per hour. So that's pretty good. So we're off. We could be off by that much. So next, we wanted to perform these tests of transferability and understand how well we did in Oregon compared to Utah. So this is the plot for all of the Oregon data. So our x-axis is the actuations, our y-axis are the pedestrian volumes. One thing to note here is most of our data is concentrated on the lower end at Oregon. We have a very few sites that have higher volumes of either high volumes of pedestrians or higher levels of signal activity. This is the Utah data, and you can immediately see the difference, right? So they have a lot more points because of their larger sample, where the activity levels are higher and the volumes are also higher. So the scales are different from the two charts. So we put both of them together on the same scale, right? And we were amazed at how well they fit together. So this gave us some confidence that these results may be transferable, right? That they line up exactly on top of each other. So then we wanted to do some actual tests to figure out, could we do this transfer, right? So we did two sorts of tests. So in the first test, we used the Oregon data, used the Oregon model and estimated our statistics. Then we used the Oregon data and the Utah model and then estimated the statistics. What we find here is that the model developed in Oregon is obviously better for the Oregon data as compared to using the Utah model, but it's not too far off. We are doing a relatively good job if we ended up just using the model developed in Utah. We repeated that test the other way. So we took the Utah data, used the Utah model, estimated our statistics, and then Utah data with the Oregon model and estimated our statistics. Again, the model developed in their own state was obviously a little bit better, but we are not too far off from the original statistics. So this led us to believe that these models are indeed transferable. So what we developed here in Oregon could be transferred to Utah, and what was developed in Utah could be transferred to Oregon. Does this mean that this could be transferred everywhere? We don't know yet. We still have to do more research to figure out what are the factors or characteristics that would enable that transferability. So in terms of conclusions, so this study basically showed us that actuation data is feasible approach to deriving pedestrian volumes at signalized intersections. And our recommended models were pretty simple, generalizable, and they transferred well across both states. There were a few limitations with the study, of course. Some of the challenges were associated with push button data, and this is actually maybe true of any data, right? So there could be some data loss or corruption issues from the equipment malfunction that could limit the data transfer. And so when you lose data, then you don't have that data to estimate your volume. So it's really important to have that data transfer going. The difference in signal operations also limits the availability of push button data, right? We did have a few locations where the signals were in recall, but they still had push buttons. So we could still get some information if somebody pushed that button. But this method is not applicable for in downtown, for example. We have no way of knowing how we can estimate volumes here when we do not have any push buttons at all. So that's a limitation. We did observe some higher errors when estimating high pedestrian volumes. And we think that is because our model in Oregon did not have many sites that were high volume. So we could not train the model appropriately in that data. So we could append and re-estimate the model using a few more locations that are more higher volume. We collected the data in summer primarily. It was great weather, but we have not investigated how any seasonal differences in actuation can affect volumes. So our recommendations from this project then were that agencies should definitely archive their pedestrian push button actuation data as a part of the ATSPM, or the Automated Traffic Signal Performance Measurement System. These data are really valuable, and they can be used more than once to generate other performance metrics other than just pedestrian volumes. And there are lots of data that are available from the logs. They are recorded every 10th of a second. So if storage of raw data becomes an issue, then you could even explore aggregating this data to larger time bins and storing it. So that would reduce your storage implications, but you could still use that data for performance measures. And then we also recommend that regular validation be performed, right? We don't know of pedestrian volumes other than the 49 locations, but we want to continue to use this model. We need to validate it and have a few more volumes so that we could ensure model accuracy. So in terms of future work, there are a lot of points on this slide. We basically used statistical methods to build our models. Obviously, there are a lot of machine learning and AI techniques right now. Those could be employed to estimate volumes. We also need to understand how frequently these models need to be re-estimated and under what circumstances. We have not done any research on that. The transferability tests were between Utah and Oregon. These are both states in the Western United States. We don't know if this behavior and the models could be transferred to other regions in the US. Don't know. We could also investigate the use of outlier detection techniques and others to fill in data when we have large amounts of data missing. Okay, I think that's it. Yeah, I'd just like to acknowledge ODOT for funding this research. Without that, this research would not have been possible. Josh Roll, who was our research coordinator and really did a fantastic job keeping us on task and expertly managed the project. Members of the TAC for providing feedback and review of all the deliverables of the project. Sean Strasser, Allison, Matt, and John, they provided us signal data that enabled this research. And there were a number of students from both Portland State and Utah State that helped us reduce the video data, hours and hours of video data. So thank you to all of them. And I think, yeah, that's my last slide. So I'm happy to take questions.
Thanks so much, Sirisha. For those viewing the webinar, please feel free to submit your questions using the Q&A feature in the control panel on the bottom of your Zoom window. And we'll go ahead now and start with questions. Anyone in the room? Can you just call in?
Yes.
There are, so you mentioned situations where there's push button, situations where there's also some shades of gray in between, right? Sometimes there's a push button that doesn't actually do anything. Sometimes there's a push button. When you say push button that is usable, I imagine you're talking about one that actually creates entire cross traffic phase change. Or sometimes there's one where the cross traffic phase will trigger, but if you want to get the PED sign, you have to push the button. Otherwise, it'll say green for cars and for PEDs, right? So there's these intermediate levels of push button application or operation. Did you use that as a variable, or did you make sure you only had really two types, none and full phase trigger? Or
Yeah,
essentially this is a behavioral analysis, right? So I imagine people might behave differently, especially people who are locals who know how the buttons work or don't work. So I imagine people might behave differently with different types of buttons.
Yeah, no, we looked at signals that were actuated. So when you push the button, call is sent to the controller and you get the phase request and phase change. And those that were, on recall. So you still push the button or you don't, but the indication will come up anyways. So if you still end up pushing the button though, you will get a row in the log, and that's what we were using. So so to answer your question about the different, no, we didn't have access to, those multiple, conditions. So we just looked at these two. There were the different variations on how the data would be recorded in the logs. And so we looked through all of them. And then that's why we ended up using those imputed measures of the signal metrics in the log, the A45B, A90C, to take care of those situations. So the one that we used, A90C, for example, is the one where it's recording the unique pedestrian detection. So every time you push a button, there are a lot of people who do that, right? So we employ like a 15-second filter to ignore any push button presses for 15 seconds after that first push button was pressed, and then we use that. Yes.
The ultimate long-term goal of the data, is it to improve, because you mentioned improving infrastructure, is this specifically crosswalk infrastructure, intersection infrastructure, is it overall PED? My thinking is not everybody crosses the streets and they might be going right, and so they're never gonna hit the push button. Some people, they might be choosing, if they need to go from southwest to northeast, for example, they might be crossing depending on whether that signal is already there. Some people might go midway and then cross. So are you concerned that if we're only looking at push button, is that accounted for in your models?
Yeah, so we looked at only volumes that or pedestrians and other crosswalk users that were within a certain distance from the crosswalks, right? Because we started off counting people maybe mid-block, but then that's not fair to the model, right? Because they might not push the button, and so you're setting yourself up for failure. So so we would maybe about 5 feet or 10 feet from the crosswalk is where we would count anybody that's intending to use it. And the main purpose of this was to estimate pedestrian volumes. Those volumes can be used for a variety of things. So it could be used, for infrastructure, for safety, for, other health, equity, anything. But we didn't look at the application side of things. Our goal was to just estimate volumes, because currently we don't have any systemic volumes anywhere. So yes.
I'm super excited with this research. I'm so thank you for presenting this. So you mentioned that next steps might be agencies, recommending that agencies archive this data. What was, if you hadn't been performing the study, did you notice that archiving is happening of any of this data?
Yes, there are a few agencies for sure that are, leaders and are archiving the data. PBOT, ODOT, they are archiving data right now. UDOT was a leader in this aspect, and they have archived this data, built a huge dashboard and different signal performance metrics that are, related to vehicular traffic and, multimodal traffic, which allows them to understand how well the intersection is performing and to improve the efficiency and the operation. So that's where they're using this data. So Utah DOT, I think Georgia is also doing it. So there are definitely a lot of agencies, coming on board. Yes.
Do you have a theory why Oregon data is so much easier to predict than Utah data? No matter what model is, Oregon model works perfect fine. Utah model works. I think it's like a 0.1 difference in R squared.
Yeah, that's a good question. Our hypothesis was that, we had a smaller set, and our intersections maybe were a lot more homogeneous than the Utah, where they had 90 intersections. They had a wide variety, of volumes and ranges. And so that's why that was our hypothesis, that maybe it's a more difficult ask of the model to predict, whereas in Oregon our data is sort of concentrated in that lower range, and so the model may be seeing that, so it's maybe a little bit more easier to predict. Yes.
I wondered if you looked a little bit at the roadway design, because if you're crossing like two left turns, and this is the crossing distance is quite a bit more, and so you're not gonna jaywalk, you know, it's very rigorous in terms of your behavior. If that had an impact of non-linearity.
Yeah, that's a good question. No, we did not look at roadway design at all because we wanted this to be agnostic of like, okay, we're just looking at the information from the existing infrastructure. How could we use that to predict volumes, whether it's a 2-lane, 4-lane, 6-lane, what have you. But yeah, but that's an interesting idea for a future. Yes.
I thought I heard you say that you also recorded timestamps when people, did you do anything with that?
No, good catch. No, we did not end up doing anything with it. We were thinking maybe we'd look at crossing times and, you know, and maybe potential delay and things like that. But the issue, and Elizabeth, please jump in if I'm misrepresenting something, but I think the issue was at some of the locations, because we had one camera angle, and if the intersection is large, it's really difficult to see like where, you know, to get those timestamps accurately. So we weren't terribly confident with it. And also sometimes the view is cut off, so you can't really see when the pedestrian's arriving, you know, at that curb and for the delay measurement. So yeah, we ended up not using it.
I have a question, like a few slides in, when you're showing the data collection methods, you said there was a criteria used to reduce the number of intersections that data had to be collected from. And rather than it just using all of them or being chosen randomly, the criteria involve things like being close to access or having at least 10 average crossings a day or something. How do you deal with the bias that criteria interjects into the data?
Yeah, that's a good question. I think we had to sort of balance that out to, you know, yes, ideally we would, you know, just do a random selection, go everywhere and collect. But, you know, realistically, we were limited, right? Like even if we went to like Eastern Oregon or Southern Oregon, we would see like 1 or 2 pedestrians or maybe 5 a day. And we figured that even with using the locations in the Willamette Valley, we could account for those broad ranges of context, right? So we were able to look at like maybe a more suburban location versus a more, you know, urbanized location versus also the lower end of the walking activity spectrum to the higher end. So we limited it for ease of data collection, but we ensured that we were able to accommodate those contexts in that. Yes.
A tiny little question. So what about loop detectors for bikers?
Mhm.
How did that ever factor into any decisions in planning this out?
Yeah, we when this project was designed, and that's why the title says the transportation counts, and it ended up, you know, just being pedestrian counts. The idea was to use data from loop detectors, but the issue I think we were running into was that it is not stored for as long as a time as these other logs. And so we would get very short, you know, bursts of data, and so we wouldn't have that information. There was also some concern about, you know, how well those loops have been calibrated. I have done some past work looking at the loop detector data and using, you know, those logs to understand how well they're working. The issue is the location of the loop really matters. And so if you have that loop very close to a right turn, it can pick up vehicles, and that can cause huge errors in your data. Yeah, so we weren't as confident with the loop just, you know, yeah, just recording bicyclists as we were with, you know, the push buttons just recording crosswalk users.
We do have a couple of online questions. And so somebody's wondering, can you confirm that pedestrian volume coincides with the PM peak hour for vehicles? And they thought that past pedestrian count research showed that peak pedestrian volume is midday or noon. and wondered what you thought about that difference.
Yeah, I think it depends on the location, right? We can generalize it, but past research has shown that anywhere from midday towards the evening hours is when the peak is. And so it totally depends on, different locations.
And then just one more kind of shorter question. Somebody's just wondering what percentage of pedestrian buttons generate a log?
That's a good question. I think it depends on the agency. So the older traffic signal controllers don't have that capability. But agencies are, installing newer controllers which have this capability of generating the logs, and then they decide to archive it. I don't think I could tell you an exact percentage because it varies by agency, but I think we're definitely moving in the right direction. Oh, yeah, Tara.
Yeah, I wondered, the impact on driving, right? So you're driving there and then you can't turn right because there's a pedestrian and then someone comes the other way. So is there any, and it seemed like you alluded that Utah was looking at the impact on the driving side as well? Not just pedestrian volumes, but the impact on that infrastructure?
Well, not through this study
Yeah,
or
right.
the similar study, but I guess what I was saying was if you collect and archive the signal logs, those have a lot more information in them. So you could calculate metrics like percent arrival on green and things like that. That will tell you how well, your signals are working for pushing your capacity through. So your
Right, like the throughput impact
Yeah.
of having a lot of pedestrians
Yeah.
versus having very little.
Yeah.
So.
Yeah, but those are different metrics, different event codes and enumerations that we didn't look at in this study. But yeah, the data is definitely available.
All right, thank you all for attending today's PSU Transportation Seminar. For those of you joining remotely after this seminar ends, you'll have the opportunity to complete a brief survey about today's event. It only takes a few minutes and we would really appreciate your feedback, so please take the survey. Join me again in thanking Sirisha so much for today's presentation, and thank all of you for joining us today.